imagine if you could like paint solar power onto your roof.
Mm-hmm.
Have it be like thin and flexible. That's kind of the promise of perovskite solar cells.
Yeah.
But there's a problem.
Yeah.
They're unstable, like
Yeah.
super unstable.
Right.
It's kind of like, if you build a sandcastle on the beach,
Mm-hmm.
it looks amazing, but then the tide comes in and it's gone.
Yeah. Yeah.
We're diving deep today into perovskites
Okay.
and, what makes them so special. But more importantly, why they keep falling apart.
Right.
So
Yeah.
this instability thing,
Yeah.
it's a big deal, right?
Yes, it's like the biggest hurdle right now for perovskite solar cells. Yeah.
So how are scientists, how are they dealing with this?
Well, there's a ton of research going on all over the world, and they're kind of tackling this problem from all different angles.
Okay.
You sent over a stack of research. We've got articles here from Nature,
Yes.
Science, Joule, Advanced Energy Materials.
Lots of good stuff.
Really, really fascinating stuff, and
Yeah.
it's clear that this is a hot topic.
Yeah, it really is.
Yeah.
So before we get into the nitty-gritty,
Mm-hmm.
can we just take a step back?
Sure.
What exactly are perovskites?
So perovskites, they're not actually a single material. They're a family of materials.
Okay.
And what they all have in common is this unique crystal structure.
Okay.
Imagine like a tiny, tiny building block with this formula, ABX3.
Okay.
Each letter represents a different element or molecule, so you can kind of mix and match them
Interesting.
and get different properties.
Oh, it's like a recipe, kind of.
Exactly. It's like a recipe.
Yeah.
You tweak the ingredients, you get a different flavor.
I like that.
Yeah, and by tweaking the recipe, researchers can manipulate something called the band gap.
Band gap.
And that's the energy range that the perovskite can absorb from sunlight and convert into electricity. So by adjusting the band gap, they can optimize the perovskite for different applications.
So it's like a material chameleon.
Yeah, pretty much.
Yep.
It can adapt and be used for lots of different things.
So you can have transparent solar panels for windows.
Exactly.
Or flexible cells that you could put on clothing.
Yeah.
Really cool.
It's really exciting stuff.
But I mean, if it's so amazing, how come we don't see perovskite solar panels,
Right.
everywhere?
Well, that's the big challenge, right? The instability. It's like they're allergic to the real world.
Yeah.
Moisture, heat, even light, all these things can cause them to degrade really quickly.
That's crazy.
Yeah.
So is it something inherent in their structure?
Yeah, I mean, the perovskite structure, it's kind of a double-edged sword.
Mm-hmm.
It gives them their amazing properties,
Yeah.
but it also makes them prone to defects.
Defects. Okay.
Yeah, these little imperfections in the crystal lattice. And those defects, they can act like traps for the charge carriers, the electrons and holes that carry the electricity. And that reduces the efficiency, and it can speed up degradation.
So it's not just external factors, it's
Right.
internal flaws, too.
Exactly. It's like, if you build a house on a shaky foundation,
Yeah.
it doesn't matter how beautiful the exterior is, it's not going to last.
That's a good analogy.
Yeah.
So let's break down these instability challenges one by one.
Okay, sounds good.
First up, moisture. It seems like even a little bit of humidity can send perovskites into meltdown.
Yeah, it's true. They're very sensitive to water.
Why is that?
Well, water molecules can actually infiltrate the perovskite structure, and they disrupt the bonds between the atoms, and that can cause the material to break down.
So what are researchers doing about this?
Well, one approach is to modify the perovskite composition itself.
Okay.
Kind of like we talked about with the recipe analogy. They're trying to replace the moisture-sensitive components with more robust alternatives.
So it's like swapping out a water-soaked sponge for
Yeah.
something that's water-resistant.
Exactly.
Okay, so how do they actually do that?
Well, it's all about finding the right chemical substitutes, right?
Mm-hmm.
So researchers are experimenting with different organic and inorganic components,
Yeah.
looking for ones that can withstand moisture without compromising performance.
Okay.
And one promising candidate is this organic acacian called formamidinium.
Formamidinium. Okay.
Yeah, and it creates this tighter, more compact perovskite structure, and that makes it harder for water molecules to penetrate and cause damage.
So it's like reinforcing the walls of the perovskite fortress.
Exactly.
Right.
Keep those moisture invaders out.
I like that.
Yeah.
So they're manipulating these materials at the molecular level to
Yeah.
create these macroscopic changes.
Exactly. It's really amazing what they're doing.
Yeah, it is.
Yeah.
But moisture is just one piece of the puzzle, right?
Well-
Perovskites are also very sensitive to heat.
Yes. Very much so.
It's like, imagine a chocolate bar melting under the hot sun.
Mm-hmm.
That's what happens to perovskites at high temperatures.
Yep.
Their structure warps, their efficiency plummets, and ultimately, they fail.
That's right.
So how are they dealing with this heat sensitivity?
Well, one approach is to use inorganic perovskites
Okay.
instead of the organic ones because inorganic materials tend to be more heat resistant.
Okay, so it's like swapping the melting chocolate for a ceramic tile.
Exactly. Exactly.
That's much more durable.
Yeah, much more durable.
But what about the organic components that make perovskite so special? Are they just out of the picture?
Not necessarily. Researchers are also exploring ways to enhance the heat tolerance of hybrid perovskites.
Hybrid perovskites.
Yeah, the ones that combine both organic and inorganic components.
Mm-hmm.
So they're looking at things like additives that can stabilize those organic molecules,
Okay.
prevent them from breaking down at high temperatures.
So it's like adding nuts to the chocolate bar to make it
Yeah, something like that.
more heat resistant.
Exactly. Provide some structural support.
Okay.
Yep.
So we've talked about moisture, we've talked about heat.
Mm-hmm.
What about light?
Yes, the irony of it all.
Yeah, it seems counterintuitive that the very thing that powers a solar cell can also be its downfall.
It's true. It's a strange twist of fate.
So how are they protecting perovskites from light-induced degradation?
Well, one approach is to use protective layers,
Okay.
kind of like, UV filters.
Yeah, like sunscreen for the solar cell.
Exactly, exactly. So they can shield the perovskite layer from the harmful UV radiation.
Mhm.
And they're also experimenting with doping, which is adding tiny amounts of other elements to the perovskite structure itself.
Okay.
And that can enhance its resistance to light.
So it's like fortifying the perovskite from the inside out.
Exactly, making it inherently more stable.
Okay, so they're really approaching this problem from all angles.
They are. It's a very multidisciplinary effort.
Yeah, that's really cool.
Yeah.
But it's not just about making perovskites more stable.
Right. Yeah.
We also want to maintain their incredible efficiency.
Absolutely. That's crucial.
So it's a delicate balancing act.
It is. You don't want to sacrifice one for the other.
Yeah.
You need both.
Right. We need perovskites that are both durable and efficient if we want to truly revolutionize solar energy.
Exactly.
So are we getting there?
I think we are. The research you sent over, it highlights some incredible progress.
Okay.
I mean, there are perovskite solar cells out there exceeding 25% efficiency
Wow.
and showing significant improvements in stability.
That's incredible. 25%, that's
Yeah.
really high.
It's really impressive.
But those are still lab scale achievements,
Yeah, right.
We're not quite there yet with
Not
the
yet.
production.
No, the real challenge is scaling up production,
Yeah.
making these perovskite solar cells commercially viable, getting the costs down, making sure they can be manufactured reliably at a large scale.
And that's what we'll be exploring in the next part of our deep dive.
Exactly.
So stay tuned for that.
Yeah, it's going to be good.
All right.
Welcome back.
So we've talked about how perovskites are, kind of sensitive to
Yeah.
moisture and heat and light.
Mm-hmm.
But it's not all bad news, right?
No, not at all, actually. It's actually quite the opposite. There's a lot of optimism in the field right now.
Okay, so what are some of the solutions that researchers are working on to overcome these challenges?
Well, let's go back to the moisture issue.
Okay.
We talked about how they're modifying the composition
Right.
to make it less hydrophilic, less water-loving.
Mhm.
It's almost like giving it a water-repellent coating.
Yeah, swapping out those hydrophilic organications
Right.
for more hydrophobic ones.
Exactly. Exactly.
But it's not just as easy as plugging in any water-resistant molecule, is it?
No, it's got to be compatible with the rest of the structure.
Right. It has to work with the whole system.
Exactly. You need that synergy. Yeah.
So what are some of the,
Mhm.
molecules that they're looking at?
Well, formamidinium is one that's showing a lot of promise.
Formamidinium. Okay.
Yeah, it's an organic excitation, and it forms this really tight, compact structure,
Mm-hmm.
which makes it much less vulnerable to water infiltration.
So it's like tightening up the defenses,
Yeah.
making it harder for the water to get in.
Exactly. Yeah, like a fortress,
Yeah.
You build those walls high and strong.
I like that analogy.
Yeah, and but it's not just the organication, right?
Right.
We also have the halides to think about.
The halides, okay.
Yeah, the negatively charged ions in that ABX3 formula.
Mm-hmm.
Those can also play a big role in moisture resistance.
Okay. How so?
Well, for example, bromide-based perovskites tend to be more stable in humid environments than iodide-based perovskites.
Interesting.
So it's really about choosing the right materials for the job, just like
Yeah.
if you're building a house in a rainy climate, you wouldn't use straw.
Right. You'd use something more water resistant.
Exactly, exactly.
So it's really about like tailoring the perovskite to the environment that it's going to be used in.
Precisely. Yeah, it's all about customization.
Okay, so, we've talked about moisture, but what about heat?
Right, heat, that's another big one.
Yeah, they tend to, kind of melt.
They do. They're not very fond of high temperatures.
Yeah, like that chocolate bar in the sun.
Yeah, exactly. It just kind of wilts away.
So how are they preventing them from turning into goo?
Well, one way is to go inorganic.
Inorganic, okay.
Yeah, so instead of using organic components, you use inorganic ones, which are inherently more heat resistant.
Okay, so it's like swapping the chocolate bar for a
Yeah.
ceramic tile or something.
Yeah. Exactly, something much more durable.
Okay, so just get rid of the organic stuff altogether.
Well, not necessarily.
That's fine.
Researchers are still working with those hybrid perovskites.
Right, the ones with both organic and inorganic components.
Yeah, because they have some unique advantages. So they're trying to find ways to make those hybrids more heat resistant.
Okay, so how are they doing that?
Well, one approach is to use additives.
Additives, okay.
Yeah, these are like special ingredients that can stabilize the organic molecules and prevent them from breaking down at high temperatures.
So it's like adding, I don't know, like nuts to the chocolate bar to make it.
Yeah, something like that. Yeah, provide some extra support.
Okay, so it's not always about complete replacement.
Right.
Sometimes it's about like reinforcement.
Exactly.
Okay, cool. So we talked about moisture, we've talked about heat. What about light?
Ah, yes, the irony of it all.
It seems counterintuitive that the very thing that powers a solar cell can also be its downfall.
It's true. It's a bit of a paradox.
So how are they protecting perovskites from this light-induced degradation?
Well, one promising approach is to use tandem solar cells.
Tandem solar cells, okay.
Yeah, these are basically cells that have multiple layers. And each layer is optimized to absorb a specific part of the solar spectrum.
Okay.
So you can have a layer that absorbs visible light and then another layer on top that absorbs UV light.
So it's like a team of superheroes.
Yeah, I like that.
Each with their own special power.
Exactly. They work together to defeat the villain, which in this case is UV radiation.
Okay, and so the perovskite layer is protected from the UV layer.
Exactly, yeah. It's shielded by the top layer.
But it's not just about protection, right?
Right. There's another benefit to tandem cells.
Okay, what's that?
They can actually boost efficiency.
Oh, okay, how so?
Well, by combining materials that absorb different parts of the spectrum, you can capture more of the sun's energy overall.
So it's a win-win.
Exactly. You get better protection and better performance.
That's really cool.
Yeah, it's a really clever approach.
So with all this focus on stability, are we sacrificing efficiency?
That's a good question, and it's something that researchers are very mindful of.
Yeah, because, at the end of the day, we want solar cells that can generate a lot of electricity.
Absolutely. That's the whole point.
So are we making any progress on that front?
We are, actually. The latest research shows that we can achieve both high efficiency and high stability.
That's really good to hear.
Yeah, it's very encouraging.
So we're talking about perovskites that can really compete with silicon solar cells.
I think so, yeah. They have the potential to be just as good, if not better.
That's really exciting.
It is. It's a very exciting time to be working in this field.
So it seems like, things are really moving in the right direction.
They are. There's a lot of momentum right now.
But we still have that challenge of scaling up production.
Right. That's the next big hurdle.
Taking it from the lab to the real world.
Exactly. We need to figure out how to manufacture these perovskite solar cells on a large scale and bring the costs down.
And that's what we'll be discussing in the next part of our deep dive.
That's right. We'll delve into the challenges and opportunities of mass production.
We've been talking about perovskites, their challenges, the instability issues, but also, their potential, the incredible efficiency gains.
Right.
It really does feel like we're on the cusp of something like a scientific revolution.
Yeah. It's an exciting time for solar energy research, that's for sure.
So we've focused a lot on the hurdles, but I kind of want to, shift gears a bit.
Sure.
And talk about the possibilities.
Okay.
Like, what are some of the most exciting applications of perovskites beyond, just your typical solar panels?
Well, one of the things that makes perovskites so fascinating is their versatility. Remember we talked about how scientists can kind of tune their properties, adjust the band gap.
Yeah, like the recipe analogy.
Exactly. And that opens up a whole world of possibilities beyond just, putting them on rooftops.
Okay, so paint me a picture. Like, what are we talking about here?
Well, imagine flexible solar cells that are woven into fabrics,
Oh, wow.
powering our devices on the go.
So, like, solar-powered clothing.
Exactly.
That's amazing.
Yeah, you could have backpacks and tents that double as energy sources.
Oh, that would be awesome for camping.
Right, exactly. Especially as we become more reliant on mobile devices and, off-grid living.
Yeah, definitely.
And it's not just about wearables and outdoor gear. Perovskites can also be made semi-transparent.
Oh, really?
Yeah, which means they can be integrated into windows without blocking out too much light.
Whoa, so like solar-powered windows.
Exactly, and imagine the impact that could have on energy efficiency in buildings.
Yeah, that would be huge.
Yeah, skyscrapers generating their own electricity.
That's incredible.
And with the potential for low-cost production, perovskite solar cells could revolutionize access to electricity in developing countries, bringing power to communities that have never had it before.
That's amazing. I mean, that would be a game changer.
Yeah, it's really exciting to think about the potential.
Yeah, it's inspiring.
Yeah.
So it's not just about, clean energy. It's about social impact, too.
Right, it's about improving lives.
Yeah, that's really cool.
And the applications don't stop there.
Okay, there's more.
Yeah, researchers are exploring perovskites for LEDs,
LEDs. Okay.
lasers, even sensors.
Wait, hold on. So we're talking solar cells, LEDs, lasers, sensors, all from the same material.
Yep, pretty much.
How is that even possible?
It's all about their unique optoelectronic properties.
Yeah.
They're incredibly efficient at absorbing light and converting it into electricity, but they can also emit light.
Oh, I see.
So that makes them suitable for things like LEDs and lasers.
Wow, that's mind-boggling.
It is. It's pretty amazing.
So perovskites are like the Swiss Army knife of materials.
Yeah, I guess you could say that.
They can do it all.
They're pretty versatile.
So we've talked about all these amazing possibilities, but I guess the question is, how do we get there?
Right. Well, there are still some challenges to overcome, like scaling up production.
Yeah, taking it from the lab to the factory.
Exactly. We need to figure out how to manufacture these perovskite solar cells on a large scale and bring the costs down.
Okay, so how are they tackling that?
Well, researchers are looking at various techniques like roll-to-roll printing and slot die coding.
So they're borrowing methods from other industries.
Yeah, adapting existing technologies and streamlining the manufacturing process.
That makes sense.
Yeah. And there's also the issue of lead.
Right. Some perovskites contain lead, which is obviously a concern.
Yeah, it's something that we need to be mindful of.
So are there any alternatives?
Yes, there's a lot of research focused on developing lead-free perovskites,
Okay.
using alternative materials that are both safe and efficient.
So it's not just about performance and scalability.
Right.
It's about sustainability and responsibility, too.
Exactly. We want to create a technology that benefits everyone, not just in terms of clean energy, but also in terms of environmental protection and human health.
Yeah, it's great to see that researchers are taking a holistic approach.
Yeah, it's really encouraging.
Well, this has been an amazing deep dive.
It has. It's been a fascinating journey.
We've learned so much about perovskites.
Yeah, it's a really exciting field.
Their challenges, their potential, the incredible progress that's being made.
And we're just at the beginning.
Yeah, I'm so curious to see what the future holds for perovskites.
Me too. I think we're going to see some amazing things in the years to come.
Well, a huge thanks to you for guiding us through this.
My pleasure.
And to our listeners, thanks for joining us on this journey.
Yeah, thanks for listening.
We hope you learned something new, and we'll see you next time.